everybody. Good afternoon or good evening, depending where you are. Welcome to this IRENA online seminar. It is my great pleasure to introduce Dr. Aswin Vijayan, who is an expert in galaxy evolution simulations, particularly in dust production and high redshift simulating and comparisons with galaxy observations. Aswin got his PhD from the University of Sussex in 2021. He then moved over to Denmark, where he was a fellow at the Cosmic Dawn Centre, and he has recently returned to the UK, to the University of Sussex again, as an STFC research fellow. And it is, as I said, my great pleasure to introduce him today. He will be speaking to us about first light and reionisation epoch. Aswin, please.
Thanks, Rob. Thank you for inviting me to give this seminar. Yeah, I'm excited to talk about some things that I've been working on with a lot of collaborators who are spread across the University of Sussex and the Cosmic Dawn Centre. And yeah, most of this wouldn't be done without their help. And also a wide variety of funding institutions. The DNRF, which supports the Dawn Center, the Carlsberg Foundation, yes, that's the beer that we're talking about, which actually funded my grant at Dawn, and now STFC, which has been supporting my research fellowship at the University of Sussex currently. So I started in April. So before I go to the details about what my work is, I would like to say a bit more about myself. I'm from India, the southernmost part of India. So if you can see on the screen, this is the area that I'm from. It's called Kerala. It's a really nice place. A lot of nature and really nice food. So if you're actually planning on making a trip to India, please do try to go and have some of the things that Kerala has to offer, like tropical rainforest, really nice backwaters. You can even rent a boat and have a trip along the waterfront. And if you're interested in fish, they would even actually catch fish for you and make it directly in front of you. So getting back to the science part of things. So as I said, this is done in collaboration with the people at Dawn and at the University of Sussex, and specifically what we call the FLAIRS team, which is the First Light and Reionisation Epoch simulations team, which have developed a suite of simulations specifically to study the epoch of reionization. And before I go into most of the details of my work, I would like to introduce what are some of the biggest open questions in this reionization epoch, and try to go through them while in the talk. So the first big question that we want to ask ourselves is, when did the first galaxies form? And this wouldn't have been possible without what we call the Big Bang nucleosynthesis, which is happened in the first few minutes of the Big Bang, where some of the light elements like hydrogen, deuterium, helium, and trace amounts of lithium were created. And these are the building blocks of galaxies and life as we know it. And moving on into a later epoch, which is the epoch of recombination, where most of the universe's baryonic content was in neutral hydrogen and helium, which started to release the CMB. And soon after, the universe entered what we call as the cosmological dark ages. During this period, there was no source of visible light, and it's very hard to access it. And we are expected to soon access this regime through 21-centimeter observations on radio telescopes, such as the SKA, which is being built in Australia and South Africa. And this is the period that we have currently been accessible through at least some telescopes. At least we hope that we have had access through JWST. So the first slide is the period where the dark ages came to an end by the formation of the first stars or the supermassive black holes and the first galaxies a few hundred million years later on, which is approximately a redshift of 20 to 30. Now, the timing and growth of these structures serves as an essential constraint on cosmology and physics in the nascent universe. So, for example, if we think about a universe with warm dark matter or cold dark matter, the timing of these structures would be quite different. In a warm dark matter universe, the structures would start to assemble slowly at first, but at later times assemble much faster. However, with less power at the low mass regime, because some of the structures would be washed out because of dark matter being warm. And then we get to the epoch of reionization, where these first stars and galaxies and supermassive black holes start to reionize mostly neutral hydrogen in the universe. And this, from current theory, happened over a gigayear of time in the universe. And you can see that this epoch has already been accessible through Hubble, as well as other ground-based telescopes such as ALMA, for example. And the next epoch is like the dawn of galaxy evolution, where there is quick enrichment from pristine first stars, which we term as population 3, transitioning to low metallicity population 2 stars, whose signatures we are currently witnessing through our telescopes. And hopefully, with the launch of James Webb Space Telescope, we are probably going to see structures far into the epoch of reionization, possibly the first galaxies in the universe. And we are currently sitting here observing everything. So what are the actual open questions in this so-called first light and reionization epoch? So the first one is, how, when, and where did the first stars form, and how different are they from subsequent generations? Another one is, how, when, and where did the first supermassive black holes form in the universe? And what was the dominant source of photons responsible for reionization of the universe? And how quick was the growth of structures in the early universe? Also, we need to understand how did the chemical enrichment, that is, the metals and dust that formed in the early universe, how quickly did this enrichment proceed? And then it's how, when, and where did these galaxies first quench? So these are a few open questions that are there that we need to answer during this reionization epoch. And how should we study these systems? Ideally, it should be between observations and theoretical models trying to solve these very big questions in the universe. So in terms of the observations, you usually stare at a patch of the universe for a really long time, try to observe the galaxy population. Usually in the high redshift universe, these are blobs of light, and we try to infer their redshift and their general properties, such as their luminosities, the fluxes in different bands, and what we get from them we might actually compare to theory or simulations, trying to understand some of their physical properties. This could be by using something like spectral energy distribution fitting of the observed fluxes from these galaxies to infer the intrinsic galaxy properties, such as the galaxy's stellar mass, for example. How many stars do they form at the epoch of observations, trying to infer what kind of star formation history these galaxies had. And there are a multitudes of physical properties that we could observe by looking at different parts of the electromagnetic spectrum. And we need the theoretical models to interpret these observations, because these observations by themselves doesn't actually give you anything. You need a framework to interpret them. So this could be something like modeling the spectra from the stellar population, such as SED fitting. And the other is through building models of galaxy formation and evolution. These can be semi-analytical models, such as the ones Rob Yates and me work on, and also others such as hydrodynamical simulation, which separately follow the evolution of gas, stars, black holes, etc. in the universe. And then finally, theory by itself is not enough. You need to compare to observation. So it's a cycle which goes through different iterations to finally get to the right answer. So before I go into many of the details, I would like to make an attempt at convincing people in the audience that why do we need simulations? So we know that galaxy evolution happens through billions and billions of years. So for example, here you have one of the, on the left, one of the earliest galaxies that has been detected by the James Webb Space Telescope. And we have obtained spectra for it. And it is about like 200 million years after the Big Bang. And you have some galaxies which are producing lots of ionizing photons. And then you have these grand spirals that have happened later on, and then galaxies which are almost dead, that is not producing new stars within them, which looks very red. So these are all the red and dead galaxies. And you could imagine this to be more like how a person goes through life. They're born, they have like a very active teenage life, probably like a midlife crisis, I assume, which galaxies go through sitting on the main sequence, and then they become very old with these red stars. So you can imagine them to be at the end stage of retirement, for example. So simulations give us one of the theoretical frameworks through which we can study galaxy formation and evolution as testbeds, using them as laboratories. And this is also because galaxies evolve at timescales much larger than what humans go through. We can follow the evolution of a typical galaxy. We can even have a statistical sample of different types of galaxies that we observe in the universe to understand what kind of process shaped them. And it's also quite noble that we are trying to understand physics at one of the grandest scale in the universe, combining atomic physics, gravity, electromagnetism, and everything. So when I and the group that I'm involved in tries to study these systems, we try to model galaxies into the observed space so that we can compare these galaxies as close to the observations as possible. So you can think of the work that we are doing starting from the left and going to the right. So we have some physics which is put into a simulation. It could be a particle-based or a mesh-based, like Eulerian, Lagrangian kind of simulation. And then we get physical properties of these galaxies through some form of detection of what constitutes a galaxy. And then you can model the SEDs of these galaxies to get the observable properties and then compare directly to the observations. So what this allows us to do is, at each stage of this process, we have quite a lot of control on what kind of physics you're putting in and what kind of free parameters there are, and the influence of these free parameters in terms of what you observe from the galaxy evolution simulations. In terms of observations, you can also go back to the physical properties by doing something like SED fitting, first using some source identification, for example, segmentation in terms of the observations. So our method is to actually go from the left to right and try to compare the simulations as close to the observations as possible. And an example of this is what was done in the Eagle simulations, where they forward modeled all the galaxies and created a full spectral energy distribution from of these galaxies. And you can see how closely it resembles a Hubble Turing fork with all these different sets of morphological distribution within the simulation, and compare it to the observations. So going back to some of the open questions that I discussed in earlier, I would not be going through all of them, but concentrate on a few things that I will be able to talk through with some of the work that I've done already. But at the end, I'll conclude with what are the current, what is the current situation regarding these open questions with the current set of observations and simulations. So I will mainly talk about how quick was the growth of structures in the early universe, how did the chemical enrichment, such as metals and dust of the early universe proceed, how, when, and where did these galaxies first quench. I will try to go through it through the framework of the suite of simulations that we have designed to study the early universe, called the first light and reionization epoch simulations. I will now try to motivate why we try to do these set of simulations. One of the main reasons is that as you start going towards higher redshift, the current hydro simulations cover quite a small volume at higher redshifts. This is because simulations usually are done in the co-moving space. For example, the largest simulation that is a hydrodynamical simulation that has been done at reasonable resolution, for example, called Blue Tides, has an area of 500 co-moving megaparsec the whole cube. And once you get to, for example, redshift of 9, in physical space, you only have a size of about 50 megaparsec. And some of the surveys that are currently available, we would not be able to access many of the galaxies which are the brightest and the rarest in these systems, with using many of these simulations that don't actually have the volume to get these brightest and the rarest galaxies. And simulations are best when you have quite a statistical sample of galaxies. So if you try to look at, for example, what Euclid would observe in its journey, you would see that, oh, okay, maybe it's not visible in this plot, but the Euclid the Euclid wide survey would cover regions across this space. And if you look at the Eagle simulation, which has a box length of 100 co-moving megaparsec, you only observe a few galaxies at redshift 6. So we need quite a bigger volume to have a statistical sample of galaxies. So what we did was, instead of picking one box, we tried to sample a wide range of different densities in the universe from a much larger dark matter only box, which is shown on the right here. So this box has a side length of 3.2 co-moving gigaparsec. So if you look at some of the widely used hydrodynamical simulation, for example, Eagle, it occupies such a small volume compared to what this bigger dark matter only box occupies. So one of the biggest volumes, the Blue Tide simulation, also occupies quite a small volume in comparison to this. So what we did was we tried to look for some of the highest over densities in the early universe within this box, and then sampled milder over densities as well. So this is a wide range of over density, so that we have a representative sample of galaxies that constitutes the whole universe. So what we did was we chose 40 regions, focusing on a range of overdensities in the epoch of reionization, with a particular focus towards selecting regions which are quite overdense, so that we have the brightest and the rarest galaxies that will be observed in the early universe. So we selected spherical regions, which are about 14 co-moving megaparsec divided by h at a redshift of 5. So then we started to generate the initial conditions of these different regions so that we can simulate them with full hydrodynamics. And this hydrodynamic prescription uses the quite successful Eagle physics, which was presented in Shea et al. 2015. And we have a baryonic resolution of about 2 times 10 to the 6 solar mass, which means that we can resolve galaxies with a galaxy stellar mass of about 10 to the 8 with about 100 star particles, which is quite good, since those are the kind of galaxies that would be observed in the early universe. Now, if we compare to what a typical mass function in the Eagle 100 co-moving megaparsec volume would look like, if we look at a galaxy at 10 to the 10 in stellar mass, you can see that if we compare it to the Eagle simulation, which is the dotted line, and what we get from resimulating and collecting all the galaxies from these 40 different regions from the flare simulation, you get about 20 times more galaxies with a mass about 10 to the 10. And if we go to even higher masses, you see that we have an abundance of some of the most massive galaxies that will be found in the early universe. So this is quite a nice exercise in showing how selecting these different overdensities allow us to expand the stellar mass function over to more massive galaxies. Another advantage of this kind of simulation is that the amount of CPU power that is actually used for running these simulations is quite low compared to running an equivalent hydrodynamical simulation of a much larger box that would allow us to get to these high stellar masses. And this increase in dynamic range at the bright end complements the upcoming new generation telescopes like Euclid, JWST, and the Roman Space Telescope. Now, if we look at how we have populated this galaxy UV luminosity function, you can see that there's plenty of galaxies when we start looking at what Euclid would observe in the wide area survey or even in the deep area survey. Okay. Now let's look at how we forward model these galaxies into the observer space. So we use a simple prescription where we assign a stellar population synthesis model onto each star particle within the simulation and calculate the amount of dust that we need to look through to see this star. So you have stars and gas distributed in the simulation, and you try to look at what is the dust optical depth along the line of sight to correct for dust in the simulation. And it's a free parameter that we use to exactly measure what is the amount of dust, and that is calibrated using the UV luminosity function at redshift 5. So if you look at this plot, you can see that this is calibrated to the Bowen's 2015 data, which is pre-JWST, of course. And there's a good agreement at redshift 5 by construction. But there is also a really good agreement as we go to higher redshift with the observations. If you look at redshift 6 to 10. And another Another observation that validates this calibration that we have done is something called the UV slope. So this is the measure of the slope of the SED in the UV space. So if you look at this SED of a mock galaxy, so this is the space where you measure the slope of the SED, and it's called the UV slope because it covers the UV space. And if you look at some of the pre-JWST predictions of flares, you can see that it agrees quite well with the observation that were around at that time. The evolution of the UV slope across redshift is predicted quite well using the flare simulations, so which is the solid line. So we have done a lot of work on these using these suite of simulations. There has been 16 papers so far, but I'm not going to go through all of them, just a few of them. So this will be talking about the UV LFs, the UV slopes, the O3 LFs or the galaxy sizes, color evolution, passive galaxies, and the metal enrichment histories. Even though I won't be talking exactly about these things, the works will be derived from what we have done in these papers. And if you have enough time, supercomputing time on it, you can also do something like this, where you can run a 2D simulation of people who are working with you in the group. And if you're keen, you can also see something like a Kelvin-Helmholtz instability happening here if you run these kinds of simulations in 2D. Okay, so let's go back to some of the open questions that I discussed in the beginning. So how quick was the growth of structures in the early universe? And so from the recent results from JWST, many groups around the world have already started preparing what looks the UV luminosity function. So the UV luminosity function is basically an account of the number of galaxies that are observed within a particular UV luminosity. And this is what Nathan Adams found in his paper in 2023. And if you compare it to the simulations, it gives a pretty good result in comparison. So this is the redshift 8 UV luminosity function, which is about 600 mega years after the Big Bang. If we go to a higher redshift, for example, at redshift 9, which is 100 mega years before, and you can see that there is about a 0.5 magnitude change if you look at a UV magnitude of about -20. And there is still pretty good agreement with the simulations at these fainter galaxy end. And at redshift 10, there's about a 0.3 magnitude change at a UV magnitude of -20. There was still pretty good agreement with the simulations at most of these ranges. And if you go to even redshifts such as 12.5, even there is less amount of data, you see that there's actually negligible to no evolution of the UV luminosity function from redshift 10 to about redshift 12.5, which is very strange and quite hard to reconcile with some of the simulations that we have done of the early universe. Now, if you plot all of them together, another strange thing is you see almost no negligible evolution in the bright end of the UV luminosity function, which is indicating that there is either less amount of dust in these very bright galaxies, or there is something extra going on such that the bright galaxies are deep. Bright galaxy shows no evolution in the number densities, which could be something like an alternative structure formation theory, which has been making the rounds in these early JWST results. And if we start looking at the surface density of the galaxies that were found in the early universe, you can see that at least in redshifts around 9 to 10, there is quite a lot of good agreement with the flare simulation, which is the one in yellow, but as you go towards higher redshift, the agreement starts to fall off. And one of the other things that you can also look at is the number of galaxies that are predicted by different simulations. And these are a really great constraint on how good your physics description of the early universe is, and allows us to differentiate between different models of galaxy formation in the early universe. And you can actually make these kinds of figures, which shows the amount of galaxies predicted at redshift 12, which are brighter than a particular flux in the F277 filter in NIRCam. And you see that except for except for the Behrouzi and Silk model, none of the other simulations actually predict any galaxies that will be detected, but we do actually detect them in the early universe. So some of these early JWST data is presenting a scenario in which there is an overabundance of bright galaxies at redshift 10 compared to the models. Other studies are also seeing this, for example, from Leung 2023. Another strange thing is, if you actually try to plot many of these observations from different groups in the same space, you see that there is actually not much consensus across many of these groups. This is because most groups actually have different types of detection algorithms, different background levels, and different parameters for how to exactly do galaxy detection and segmentations within the data that are actually given. So this is a table from Nathan Adams, which shows the overlap between different studies at higher redshift. And you can actually see that the percentage of overlap is quite low in different studies. So different studies are finding different number of objects across different redshifts. Okay, let's go on to the other question. How did the chemical enrichment of the early universe proceed? So theoretical models such as flares already show that there is high levels of metal enrichment in the early universe if you go to the more mass event. And this is usually done through using line ratios such as O3, O2, or N2 to predict what is the amount of metals in these galaxies. And what many of the studies from the early universe shows us is that there is actually a dilution of the amount of metals as we go towards higher redshift. For example, the study from Nakajima 2023 and for Heinz 2023 as well at redshift 7, compared to what you found in the compared to what we found in the low redshift universe. Now, these are actually measurements which look at star-forming regions of high redshift galaxies. And these are mostly very young regions. And this allows us to understand what is the ISM conditions in the early universe. And what we have seen, for example, from a paper by James Trussler, is that the ISM conditions in the early universe are quite different from what you see in the low redshift universe. So these blue data points are from SDSS, while these are from, the contours are from flares, and the observations are the scatter points. And you can see that they occupy pretty different space. So the conditions in the early universe are quite different. And this is also seen from a study by Cameron 2023, where the redshift 5 stack of galaxies exhibits quite different line ratios compared to the redshift 6 or 8 galaxies. And what we have also seen from the early observations is that the high redshift galaxies are quite clumpy. So you can actually see bright spots interspaced by diffused points in the observation. So these are lensed galaxies, which allows us to see clearly the distribution of light from these galaxies in the early universe. And you see that there is these light dominated by clumpy star-forming complexes. And one of the issues that these create is called outshining. And if you try to fit the light from these galaxies pixel by pixel, and if you try to fit an integrated light profile, you get masses for the galaxies that are quite different from what you get by doing something like a resolved SED fitting. So this is also creating tension with lambda CDM. So there's another headache that we have to deal with when dealing with these kinds of data. And there is also a lot of discussion about what is the amount of dust obscuration that is in the early universe. For example, Hideo Alhara in his 2023 paper showed that there is actually a lot of obscuration that is happening in the early universe at around redshift 7. This was using ALMA data. And if you try to compare it with what observations see, that is an interesting avenue to understand the amount of dust obscuration that happens in the early universe. So this on the right is a set of mock observations that we have done with the flares data. And we see that you can pretty much mock the observations quite well when you compare it to the actual observations on the left. And what these mock observations tell you is that the amount of spread in the obscuration of light from young stars is very different across the galaxy. So this is a plot of the spread in the obscuration of light. So if you are at 0, there is low levels of dust, which means that there is the same amount of dust obscuration throughout the galaxy. And if you are sitting closer to 1, it means that there is a lot of spread. That is, some regions are fully obscured and some regions are completely unobscured. And what this introduces is a problem in interpreting, for example, the line emission from galaxies. And to understand this a bit better, I tried to make a toy model using the Backpipes SED fitting code. I used it because the idea was inspired by a discussion I had with Adam Carnell during one of the meetings, who is the maintainer of the Backpipes SED fitting code. So what I've done here is I have made galaxies within an SED, within this SED fitting code by making different stellar complexes. So there are about 50 different stellar complexes within this galaxy. And what I did was I assigned the same amount of dust obscuration for these 50 stellar complexes and tried to understand how varying the amount of dust obscuration along the line of sight gives you different attenuation curves. So for example, when you have the same amount of dust obscuration along different lines of sights, you get your input properties of the dust attenuation curve back. But once you have a system which is quite porous, usually described by these clumpy galaxies that we found in the observations, you see that the dust attenuation curve starts to flatten off. And if you have too much difference, then you get to something which looks like a very flat curve, which is usually called the Calzetti starburst attenuation curve with a different slope parameter. If you follow what attenuation curve is.
5 minutes left, Ashwin.
Yeah. Mm-hmm. Yeah. So what this okay. So what this introduces is a problem in interpreting these emission line ratios. So if you know what the attenuation curve is, you can try to get back what is the level of obscuration. But once, so these green points are galaxies which have the same amount of dust obscuration along different lines of sight. But once you start to vary AV, you see that these points starts to fall onto a curve which has a very flat attenuation law. And what happens if we change the ages of these star-forming complexes? It still follows a very flat attenuation curve. And what if we change the AV, the dust obscuration along the lines of sight, and the metallicity? You get a much flatter attenuation curve as well. And if you put the Flair's observation, the Flair's mock observations in, you see that it actually follows what we get from a clumpy distribution of dust and stars in the universe. What is the implication of this? So these kinds of these kinds of H-alpha lines are used to understand what is the amount of star formation happening within galaxies, because these are recombination lines and are pretty much an indicator of the amount the amount of photons within ionizing photons within the galaxy. From theory, we already know what is the ratio between H-alpha and H-beta, which can be used to know the amount of dust obscuration along the line of sight. So if we change from a normal geometry to a clumpy geometry and try to understand what is the intrinsic emission coming from the galaxy, this can only be achieved by assuming a priori an attenuation curve, and the attenuation curves that are assumed in the early universe doesn't account for this clumpy geometry that is happening within these galaxies. So we are missing quite a lot of star formation that is happening in the bright end of the galaxy stellar mass function. And this implies that we are missing a lot of star formation that is happening here. But what if we just look at the brightest galaxies? And if we look at the brightest galaxies, we see that there is about half of the star formation is not recovered. So this is a problem which we've been trying to account for by, using a master student who's working with me by looking at the UV to the optical part of the spectrum as well as the infrared. We've been using mock observations from the flare simulation, looking at NIRCam as well as ALMA mock observations, trying to understand how we can mitigate this by using panchromatic observations. So this is also an issue when looking at something like the BPT diagram. So if we look at the intrinsic value of these lines, you can see that these are here, while if you start to put dust obscuration, that is clumpy geometry of stars and dust, you see that it actually moves away from the intrinsic values to much different values. And this can actually cause us to improperly classify galaxies that fall onto different spaces when you look at these line ratios. And this is going to be a problem when we try to look at what are the ISM properties, since these can be affected by the dust along the lines of sight. So now we can move on to look at how, where, and when did these first galaxies quench. And what we have seen from the flare simulation is that supermassive black holes or active galactic nuclei within massive galaxies are responsible for stopping star formation in these galaxies in the early universe. So here is a sample of 2 galaxies that I've taken from flares. And if you look at this plot, here you can see in yellow this massive spike in the amount of activity the supermassive black hole within the center has, and the sudden decrease in the star formation activity. So this is quite common in many of the galaxies that we have looked at in flares. There's another galaxy where the star formation rate drops abruptly after an episode of AGN activity in there. So what we see is that supermassive black holes are the main culprits in reducing star formation or killing off star formation in these early galaxies. And where do these galaxies first quench? So the flare strategy allows us to look at wide range of environments, ranging from these low density environments into these extreme high density environments. And we see that the first galaxies that are quenching were biased towards regions of extreme overdensities. So this is an area where flares is quite useful, because these kinds of regions won't, these kinds of galaxies won't normally exist within typical hydrodynamical simulations. But there are also outliers where there are galaxies which have been quenched by just supernovae activity, because these are quite low mass galaxies. And this is one of the earliest galaxies that we have observed that has quenched at redshift 7.3. It has a stellar mass of about 10 to the power 8.7. And we believe that this is probably a temporarily quenched galaxy, because of how low mass it is, and because of stochastic star formation activity that happens frequently in the high redshift universe.
If you could wrap up now, Aswin, that would be great. Thank you.
Yeah. So we are also seeing quite a lot of early supermassive black holes within these observations. There are a lot of faint AGMs, and it broadly agrees with the results from hydrodynamical simulations. And I'll try to conclude with answering some of the open questions that I asked in the earlier slides. So how, when, and where did the first stars form, and how different are they from subsequent generations? Have we answered that? I would say we haven't. We're still figuring it out. We have looked at how, when, and where did the first supermassive black holes form, because of lots of faint AGNs that have been observed in these observations. We think maybe we do have a starting point to go from. What was the dominant source of photons responsible for reionization? I didn't talk about it, but from observations and from the simulation, we know that it's stars, but we need more spectra. How quick was the growth of structures in the early universe? We've been, because of how hard it is to measure the galaxy masses, we've been coming out with different observations of about depth of lambda CDM every week, but it provides quite a lot of exciting promises. How did the chemical enrichment of the early universe proceed? We see a diluted universe also showing strong dust obscuration. How, when, and where did these first galaxies quench? We see that it's stellar feedback-driven starvation as early as possible in intermediate galaxies, maybe temporarily quenched, and AGN feedback in massive galaxies. Yeah, I leave you here with the conclusions and the answer to everything. Thank you.
Great. Thank you, Aswin.